So let me do a few other examples in a different application. Let's look at something like, say, sodium. We'll do the same thing, pull out your periodic table, and this is a good example. If you want to try this first, pause the video, and then see if you get the same thing I get. So we start in the upper right, put electrons in the first s orbital, 2 electrons, 1s squared. We have to go to the next period. Now we're putting electrons in the 2s. Again, it holds 2 electrons. Go across to the 2p in the same period. That holds 6 electrons, and go back to, of course, with sodium, I should have said we hold 11 electrons total. We've used 10 so far. So the next S subshell is going to be the 3s on the third period. It only holds 1 electron, so the 3s1, and we're done. Something like, let's go across to, let's say, sulfur. Of course, sulfur has 16 electrons. We do the same thing. 1s squared. We have to go to the 2s squared. And again, it's a good time to pause and do these yourself before I show them. And now we go across the second period to the 2p. So 2p6. And it doesn't look like it. All these the SPDFs are actually lowercase to be proper. Can't always tell the way I'm writing them here, but it should be lowercase. Go across, now we finished up the second period, then we'll go to the 3s, of course 3s squared. Now we go across and we go to the 4p. I'm sorry, I said 4p. Try that again, do it properly. 3p, and we have 4 electrons more we haven't used yet, so this subshell can hold those 4 electrons. So this shows us the configuration of the electrons for a sulfur atom. Let's take something like, I say scandium. For scandium, we do the exact same thing. In this case, we have 21 electrons, so don't know what I was thinking there. 1s squared. Have to have 2s squared. We keep going across again to the 2p6, 3s squared. Now, of course, our 3p has to be fully filled, so 3p6. We start the next period. Now we're into the 4s. That's fully filled. Now we go to the d. Remember that the first s is a 1s, the first p is a 2p. The first d is going to be a 3d, even though it's on the fourth period. It's 3d, and it can hold up to 10 electrons. Remember, 5 orbitals, 10 electrons, 10 spaces wide on the periodic table, and this holds 1 electron for scandium, so it's 3d1. And that's all. So if we go across, I'll do one more here. Let's look at, say, germanium. Atomic number 32, so it has 32 electrons. 1s squared, 2s squared, 2p6, 3s squared, 3p6, 4s squared, 3d, remember. Now it's 3d10 since it's fully filled. But now we go back to the 4p. Remember, every row has to be the next energy level up. And we have 2 electrons in the 4p to use all of our 32 electrons. One thing that's good to keep in mind when you're done with this is add up all the superscripts. We have 2 plus 4 gives us 10, plus that's 12, 18, 20, 32. I've used 32 electrons. I should have 32 electrons with germanium. It's just a good way to double check that we use the right number of electrons. Again, it's just an accounting thing, but it helps you keep track of at least use the right number of electrons. Again, with things like this, it's hard to get partial credit with the configuration, but at least if you use the right number, you can get some credit for it. But that also helps you double check. At least you haven't made any egregious errors in doing this. So Back up there. So there are some exceptions to the expected configurations. This is because in some cases electrons shift from one subshell to another to find a more stable configuration. Back when we showed, let me get back to, sorry, slow computer for some reason today. Well, it's so sluggish, but anyway, back here. Oh, let's quit that. All right, back here. This shows the relative energies of, oh, I won't do that. This shows relative energies of individual orbitals, or the sublevels. These are not static energies. It ends up, you know, think of the atom as a dynamic animal. As you add electrons to it, everything changes. That's why the simplest version of our electronic, or our understanding of the atom, the Bohr model, only work with one atom, with one proton and one electron. When you add electrons into them, everything gets messed up. Same thing with these guys. When we add electrons to them, they actually can shift up and down in energy slightly, depending on how the electrons behave, depending on how many electrons they have in them, or how many electrons the neighboring orbitals have. So you can have these things shifting back and forth sometimes, and some are so close together that we can get, you know, some perturbations from what we expect to happen. So what happens is, having fully filled or half-filled subshells can be preferable to other fractions if we can have electrons shifting between subshells that are of very similar energies. By that, let's look back at one of these exceptions and I'll show you. Let's look at chromium. And let me go over to the other and draw chromium down here. A little bit easier to draw over here. Chromium, let me page down. Well, there's some more space here. Chromium we expect to be almost the same as scandium. So 1s squared, 2s squared, 2p6, 3s squared, 3p6, 4s squared, and we expect this to be 3d4. That's what's expected. In real life, we can actually use spectroscopy to figure out how these electrons behave, look at the energy states that they occupy, and what we really have is 1s squared, 2s squared, 2p6, 3s squared, 3p, oops, sorry. Write that so you can read it. 3p6, one of these s electrons actually hops over to the d, so we actually get 4s1, 3d5. The reason is, think of it in terms of what electrons are. They are negatively charged particles. Negative particles repel each other. So we have, if we look at think about the 4s and the 3d orbitals. We have one 4s orbital and 1, 2, 3, 4, 5 3d orbitals. They're all very similar energies because these are when these shells start overlapping. Now, it ends up that if we have well, I guess you can think about it in terms of symmetry. Nature in many cases like symmetry. These s electrons in this orbital are in the same orbital. They repel each other. They want to be near the atom, but negatives repel. In the d, we have 5 orbitals. One of them is vacant. So that guy decides he would like to hop over to that 5th orbital. So now we have, instead of having a fully filled subshell and one that's 4/10 full, we get 2 subshells that are exactly half filled. That puts 1 electron per orbital. So what it does is it spreads the electrons out away from each other, and that really is what makes the atom a little more stable. So that's where we get an exception in many cases for these guys, and quite often for these guys too. By the same token, they often have an S electron hops over to get a fully filled D and a half filled S. And if you're not sure about that, work it out yourself. As far as exceptions, for 104, I don't expect you to know the exceptions. I want you to know that they exist. I'll account for chromium either of those configurations as correct on an exam, so I don't want you to stress about memorizing which ones are exceptions, which ones aren't, but you should be aware that that fully filled subshells, if we can make fully filled and half filled subshells versus other fractions, that tends to make the atom more stable, the electrons more stable.